Welcome to the Unit 7 Skill 65 video for Algebra 2. Skill 65, I can graph exponential and logarithmic functions. In the first section of this unit, we learned about exponential functions, and one possible exponential function might be f of x is equal to 2 to the x. And if we were to graph that exponential function, we know it's growth function, and it winds up looking approximately like that. If we wanted to graph the inverse, then in the second skill of the section we learned an inverse is a mirror image along the y equals x line. So the inverse function of f might look something to the effect of a curve that does something like that. And that's our exponential growth function. If we have an exponential decay, we might get a different scenario. If we had the decay function g of x is equal to, we'll say, 0.5 raised to the x power. This is a curve that's going to decay and get closer and closer to the x-axis. The inverse again is a mirror image across y equals x. So the inverse of this function is a little bit harder to picture, the mirror image, but it does something kind of like that. So today what we're going to do is look at these two graphs, a decay and a growth, and look at the inverses of the exponential, so the graphs of the logarithms. We'll begin our notes on page 65A, and these notes is just going to consist of walking you through two example graphing functions and their inverses. So let's take a look at our first function, which is f of x equals 1 times 2 to the x. And let's zoom in on this. Like all functions, one possible way to graph the function is to fill out a table of values. Another possible way, which I have been teaching in class, is to actually, for an exponential function, list the sets of ordered pairs, which is more or less the same thing as filling out a table. So with an exponential function, our first ordered pair is our y-intercept, which occurs at 0, a, and in this case a is 1. So 0, 1 is our y-intercept. Every time we move to the right, we're going to multiply that value, the 1, by our b. And since b is 2, we multiply it by 2. So 1ab occurs at 1, 2, and then 1ab squared occurs at 1, 4. Moving the other direction, we have -1, a divided by b. So a is 1, 1 divided by 2 is 1/2. So at -1, 1/2, we have that point. And each time we move to the right, we're going to cut that value in half again, or divide by 2 again. Scrolling to the other side of the graph, we can see what the inverse looks like. So if we shift our paper down, the inverse is a mirror image along that diagonal. So we have a mirror image of our graph. So 0, 1 gets mirrored and becomes 1, 0. 1, 2 gets mirrored and becomes 2, 1. 2, 4 gets mirrored and becomes 4, 2. So the pattern for graphing the logarithm is more or less the same. You can see I've just switched the x-coordinate and the y-coordinate, and what I have here is 1, 0 is our x-intercept, and then we do b, 1, b squared, 2, b to the third, 3. And if we're going in the backwards direction, we do 1 divided by b, comma, -1, 1 divided by b, comma, -2. Our base is pulled from the base of our logarithm, and this pattern will always work. So our 1, 0 is located right there. Moving down, we get 1b, comma, -1, which is right there. Sorry, 1 over b, comma, -1. b, comma, 1 is right there. b squared, comma, 2 is right there. So in the inverse of the exponential growth equation, we get a logarithm that does not cross the axis, or sorry, it does not cross the exponential. It does not cross the y-axis, and that has to do with the domain and range. And if we take a look at the domain of an exponential function, the domain of our exponential function is going to be all real numbers. However, the range of our exponential function is all y such that y is greater than 0. And we can see that in our graph to the left here. Our domain, it goes forever to the left and forever to the right, and so it makes sense that x is all real numbers. It keeps going back and forth. Whereas our range, the lowest it can possibly be is right next to 0. So y has to be greater than 0. If we were to flip that, flip our domain and range so that we had a domain of x is greater than 0 and a range of all real numbers, then we're talking about the domain and range of the inverse, which we have here. Our x is greater than 0, so all logarithms are positive, and the range is all real numbers. This line goes down forever, down to -infinity, and it curves upward forever to y is positive infinity. On page 65b, I've shown an example of a exponential decay function, and the decay function is going to decrease as we move to the right. And so when we mirror that over the y equals x line, we get the inverse, and that happens to be a logarithm with a base less than 1. The same method applies for plotting the points. We have 0a happening at the intercept. We have -1, comma, a over b happening there. 1, comma, a, b happening right there. If we are to follow the same pattern for our logarithms, then we get the same points as well, plotting out like this. The key idea or concept of this skill is simply being able to graph very cleanly an exponential function and an inverse function. So if we did the exponential growth, we are going to wind up having something that starts near 0 and grows as we move to the right. When we graph this, we are going to want to have a minimum of 5 key points so that I can see that you understand how the graphing occurs. Graphing the logarithmic function similarly will start close to the y-axis and go upward and to the right forever, and we will also need to have 5 key points listed. And it's not enough to just pass through the point, you also have to list the coordinate. This happens at -1, comma, 1/2. Thank you.